I'd like to thank the organizers for including me in this exciting and comprehensive meeting with the Molecular Pathology Association. My goals today is to review the basic concepts of conventional cytogenetic analysis, along with the references to hybridization and fish testing, and show the impact of automation and what has potentially been a labor-intensive activity. Standardization, automation, and miniaturization are bywords for increasing efficiency and throughput in laboratory environment. And the simple liquid-based chemistry and immunoassay workflows in clinical diagnostic labs have undergone this transformation. Cytogenetics has, however, lagged behind on this due to lack of accurate, reliable, and reproducible technologies to automate processes. New technology can now address the challenge of bringing cytogenetic and fish workflows into the 21st. Let's start at the beginning. Watson and Crick. April 25th, 1953, the structure of DNA was established. Not long after that, in 1956, we established the correct number of chromosomes, that's 46. This is basically what our material looked like in the early 60s. No bands were on the chromosomes, but we were able to identify the chromosomes based on the length of the chromosome, position in the centromere, and we're able to group these chromosomes into groups to identify. Those of us who were at Roswell Park in the early 60s were already working on looking at chromosome changes that were required as part of the disease process. This is my mentor, Avery Sandberg, who was one of the first to make that association between hematologic disease, solid tumors, and chromosome abnormalities. So what sorts of chromosome abnormalities were observed? They were mostly mitotic events of abnormal segregation and chromosome breakage. Abnormal segregation led to gain and loss of chromosomes, while chromosome breakage led to rearrangements, deletions, or inversions of chromosomes. And as a result, in the early 1960s, Noel and Hungerford reported the existence of a small chromosome, which they termed the Philadelphia chromosome, which was the result of reciprocal rearrangement between belonging to chromosome 9 and belonging to chromosome 22. This Philadelphia chromosome actually represented one of the first observations of chromosome changes associated with hematological malignancy, in this case, CML. This lovely group of cytogeneticists and molecular biologists came together in the city of Philadelphia to honor both Peter Noel and Janet Rowley on the 50th anniversary of the description of the total chromosome. Dr. Rowley, in 1973, made the observation that this was a reciprocal mutation between chromosomes, which was not appreciated by the organic material that Dr. Noel put in. So let's review how chromosome analysis actually is performed. Many molecular biologists and pathologists are unaware that you have to have a source of dividing cell in order to visualize chromosomes. And this is important because we are always interested in the mitotic stage of the cell cycle, which normally would take about 1 to 2 hours. It's a pretty small window of opportunity for us. And we're looking for the chromosomes to be most condensed. The stages of mitosis are prophase, metaphase, anaphase, and telophase. If a cell is not actively in division, it is considered to be an interphase nucleus. And we are using those interphase cells as a target for many of our fish stuff. And if you can notice, we have spindle fibers that are attaching to the centromere region of the chromosomes and will be pulling chromatins, the sister chromatins, apart as the cell traverses from metaphase to anaphase. This is an important concept for us to consider. This is the carrier rate. This is the organization of chromosomes paired. Each chromosome pair represents a chromosome inherited from mom and a chromosome inherited from dad. The chromosomes are organized in such a way that they are largest to smallest. And this was done by early nomenclature groups, and they also were able to identify the bands on some of the signs to great works. You should also know that the position of the centromere is also useful in identifying the chromosome. Those chromosomes where the centromere or the primary construction is at the center of the chromosome, the left side of the chromosome. Those chromosomes where you can see a distinctive shorter and longer net subunits of your chromosomes. And those chromosomes, 13, 14, 15, 21, 22, are considered to be adversely chromosomes. These chromosomes only appear to have a long arm. The organization of the chromosome is pretty much standardized, and an experienced technologist is used to identify the chromosomes. This requires a lot of training in a laboratory of about 2 years in order to identify all the chromosome changes associated with cancer. So how is this analysis performed? There are several steps. The first step involves cell culture. The second step involves harvesting. There's a slide preparation step, a banding step, and an analytic step. These take at least 1 to 2 days to be completed in order to do a complete chromosome analysis. The cell culture takes place usually overnight, but can extend up to maybe 96 or more hours, depending on the cell location that we're looking at. We will take a mitochondrial as I use the book to help us accumulate more cells that are in sources. The harvest step involves adding a hypertonic solution, which allows the cells to swell, which incidentally was the step that allowed Tigeau and Levan to calculate its chromosomes in the material is centrifuged and re-suspended in multiple washing liquid, which is a very simple liquid with 3 parts methanol and acetic acid. This material is then physically dropped down to a glass slide. The slide is dry. The material is dipped in the trypsin solution to introduce the banding pattern, and then stained with bleach stain to introduce the G gating, and then analyzed by my process. So let's just kind of go back. Every cell culture that we perform in our laboratories, we like to use cells in a concentration of about half a million cells per mil. Tissue culture requires a lot of reagents, some of them very costly in serum. We our feline cysteine coordinator that is used worldwide was actually developed here at Roswell Park. You may not be aware of that, but this tissue culture medium that was used to grow multiple bags of cells in the early 60s here at Roswell Park. Serum supplementation is often very important in tissue culture, and we use up to 17% serum in our culture media. One material is harvested. The fixation takes place usually in a chemical input to avoid nitrogen cells in the laboratory. And then the material is physically dropped onto a glass slide. And that's where we tend to refer this as an article as well as science, because the article is spreading these chromosomes so that the chromosomes are not only this. There is some instrumentation there that helps us with the spreading. In those climates where it's very humid or very dry, we can control those conditions by using control channel information, which we can dial in whatever temperature we can give you as process spread. We can manually stain slide, and prior to 1990, you probably would have photographed your chromosomes through the microscope and cut them out. We do this exercise with students now, but we now have the opportunity to use a camera that's on top of a microscope. We started out with a CPD camera that actually captured the image and used software that allowed us to create a daguerreotype by just clicking and moving the chromosomes around into that period template. We now have a different level of sophistication where we can actually use an algorithm in a program that allows us to actually locate the metadata on the place, which is a tremendous time saver. So this is probably one of the first points that I will highlight in terms of time savers in the laboratory. This is something that can be done while the tech is doing another analysis, working on any other study in the laboratory. The slide is scanned at a fairly high speed, and images are captured. We can then click on the thumbnail, and then to be completed. This is just a little close up of the actual that we're using, and analysis can be completed very quickly using the software that we have. We can use the archive, it can be stored in the cloud, as opposed to a program that used including 4 years ago. We have had great success with conventional cytogenetic analysis, but it can be limited. There is always an issue with the number of cells that can be in the division. Cells from patients with acute myeloid leukemia are fairly well in culture, but as you change lineages, there's less success with patients with ALL, and even less success with cells that are more differentiated along the B cell lineage, such as multiple myeloma or chronic lymphocytic leukemia. So we've been able to take advantage of being able to correctly label the clinic gas approach and to look at a target sequence on the microscopic slide. And that target sequence can be on an interphase, non-dividing or within the metaphase itself. It's a fairly simple procedure. It can take several hours or over weeks. The example that we have here actually is piece of tissue. We can use formula fixed embedded material as well as material that we've already used for the chromosome analysis. The material is denatured using characterization apparatus and washed with several different solutions, which will then allow us to visualize the image through the fluorescent microscope. This is one of our highlights that we're using. Thermobright is the manufacturer name that Life uses, and we can put 12 slides in this sort of scenario, and we can set temperatures at varying temps based on the type of material that we have. The fluorescent analysis can be done manually. Perhaps some pictures of automation later for you. And this is a typical image that we could see that would be a dual color real fusion probe for the 9.2 iteration that we just saw by conventional cytogenetics. These are the interface nuclei, and the arrows are pointing to cells that are convoluted arranged. Chromosome analysis has continued to be an important portion of classification of tumors as well as hematologic malignancies. 3 recent papers that have come out with leukemia and blood in the past couple of months reanalyzing the classification of both myeloid as well as lymphoid malignancies, and they all continue to include chromosome analysis. And particular chromosome changes in acute myeloid leukemia are still diagnosed for some of those leukemias. And that would include the H21 and the inclusion 16 different cells. The lymphoid neoplasms have also been reorganized and reclassified, and they also continue to show chromosome abnormalities as important indicators of the disease. There's also been some discussion of developing classification of hematologic neoplasms in this area of precision medicine. It's very important now to include molecular changes on a lot of tumors as well as hematologic disease. But the basis for many clinical trials still remains to be analysis. And this slide actually does show the significance of the type of chromosomal change that you will see showing good risk cytogenetics in 1517 to 21 and 16 with the poorest risk chromosome abnormalities and AML being third abnormalities involved in chromosomes 5 and 7 and unfortunately the chromosome 3. Recently, a group of cytogeneticists initiated a discussion of where cytogenetic testing is going for hematologic malignancy. And a lot of the discussion is based on the availability of talented individuals to perform these studies. In a sense, you have an issue of time-consuming testing as well as talented staff who are experienced enough to recognize these chromosome changes. Automation is finally reached cytogenetics. This is Biodoc Accelerator. It allows us to actually deposit a very small amount of cellular material on as few as 200 interphase nuclei can be dropped onto the slide, as well as allows us to put material for conventional chromosome analysis on these slides. The biggest saving, though, with this sort of technology may be in the use of probes and the need to use far less probe material on a slide. We're all very aware of the cost of these molecular cytogenetic probes. Most laboratories will deposit anywhere from 2 to 10 microliters of probe onto the slide for a targeted area. This technology will allow us to use 0.5 microliters of material. So this gives immense saving. It also will allow for probe inventory management, coding of slides as well as drives. The nanometer dispensing will also allow for the deposition of material with 8 different probes on a single slide, again, under the statements. Another company has a little jigger process here. This is Cytogenetics little jigger, which allows you to automate the wash conditions for both conventional cytogenetic banding as well as for efficient access. You can also increase your efficiency of hybridization with some ovens as well as sliding conditions also have reduced. Let's you think that automated systems for chromosome analysis are fairly new. I ran across this document in July 4th, 1976, where the Jet Propulsion Laboratory at Caltech actually proposed an automated system for chromosome analysis. We now have the capacity to do high-speed carrier and associated with the high-speed carrier coding in the complete system, which will also allow you to automate spot counting related to the fish. And the material on the left shows a tissue section. The material on the right are individual interface nuclei that can be categorized by. But probably the most exciting change that we've seen in cytogenetic analysis would be the use of artificial intelligence and deep neural networks. A group in Germany proposed using deep neural network and artificial intelligence to perform curative analysis. This was reported as an abstract at the American Society of Hematology meeting in 2020. They used 100,000 manually placed carrier types as a training set. They then used another 500 sets to see if they could reproduce the same analysis. And they were very successful, 98.6% accuracy, with only chromosomes 4 and 5, and 14 and 15, which are commonly confused by experienced technologists as well. So where is the saving going to come in? Well, if an experienced technologist is performing chromosome analysis in their own stuff, it'll take anywhere from 1 to 3 minutes. This system will record the accuracy in 1 second, allowing then maybe about 30 seconds for that experienced technologist to check the accuracy. They're in the process of doing studies where they're performing training stuff for different structure levels, whether that be the 2, version 16, solution 5, and version 3, it's commonly with chains. So then you ask the question, how about those very complex characters? Those are always going to be analyzed by the analyst, the experienced analyst. But where the savings comes in is all of the normal cells and the placement of the normal chromosomes, even in those complex cases. So we're now seeing where our business is going. And I'll take end of this particular slide on our alternate cytogenetic stuff. I hope that you've appreciated this discussion of innovative solutions that reproduce the art and science of cytogenetic analysis. This is a slide that I've had since 1985, which talks about our alternate cytogeneticist who was hoping to attach the computer to the microscope to assist in the analysis. And those of us who do cytogenetics are usually in pathology departments. We are dealing with our medical oncologists. Tissue culture has remained constant, and our photography is now digital. But our greatest changes, of course, have been in the molecular biology. I'm happy to answer any questions, and thank you for taking us through clinical cytogenetics.